at the heart of the technique is we move along the linearization to predict the next value of y1, then move along the linearization at that value of x1, y1, until we predict y2, and now finally we get to the y value where we desired when x was equal to something in particular, I don't know what. So I hope you understand that, and that's okay.
That's okay. That's okay.
Oh, good. I'm glad that's okay.
Well, that's okay.
Well, good. So, the process of moving along the tangent line like that is called Euler's method. So, here's what we're going to do. We're going to approximate what is y of 1. In other words, what's the value of y when x is 1 for y prime equals y minus x. And yes, I know we got other ways we can solve that, but let's maybe solve it one of the other ways after we've seen what this numerical method can do for us, okay? We're going to start with the initial condition, y0 equals 2, you need that. And we're going to say let h, the amount that we bump x over by, equal 1/4. So our y1, our first predictor, is h, which is 1/4, times f of x sub 0, y sub 0. Well, this is x sub 0, this is y sub 0, and so f of that is y prime. This is going to be 2 minus 0. So that's going to be h 1/4 times 2 minus 0 plus y sub 0, and that's 2. So 1/4 times 2 minus 0 plus 2, and that is 5/2. So our first predicted y, which is predicted for the value when x is 0.25 or 1/4, remember, because we added 1/4 of 0, is 5/2. And then we move along that linearization and say, well, let's see what y2 would be. Well, it would be 1/4, that's always the same, times f of x1, y1. Well, this is y1, and x1 is 1/4 added, that was, the 1/4 that was added to 0. So therefore this is going to be 1/4, this is going to be y minus x, that's 5/2 minus 1/4 inside the parentheses, and then plus y1, which is this, 5/2, right? That's what we calculated in the last step. And if you did all the arithmetic on this, I use my software, honestly, I did 49/16. So then what? Well, we say y3, which would be the y value when x is 3/4. We're going to say, well, 1/4 times the 49/16 that we found here. X is now 1/2 when we're using the tangent line at the point 1/2 49/16 to predict the value of what y is when x is 3/4. So and then we add, of course, the 49/16, and that comes out to 237/64. Are you keeping track of this? Anyway, our y to the fourth, which is going to be the value approximated for x when y is 1. I'm sorry, the value approximated of y when x is 1. We would use this as our y. This is our x 3/4 because it's 0 plus a fourth plus a fourth plus a fourth, so 3/4, and then plus this value of y0. So, and if you do the arithmetic on that, trust me, it comes out 1,137/256, and that would be our y4, which is the value we're approximating, or we're using to approximate the value of y when x is 1. As you can see, we're getting something like 4.44 blah 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 blah. So you get that?
Uh-huh.
Okay, great. So if you got that, I think it would be worth taking the time and trouble to one time do the same problem but use a different step size. Is that okay with you?
Uh-huh.
Okay, well, what we're going to do this time, we're going to say the same problem as this one, but instead of h equal 1/4, we're going to say let h equal 1/10. Of course, y0 is 2, and we'd say first y1, which is the value of y when x is 1/10. We're going to approximate that by using the tangent line at the point where x and y are both 0. So that means h, which is 1/10, times f of x 0, y0, which remember was, that would be 2 minus 0, so 1/10 times 2 plus 2, so 1/10 times 2 plus 2 is 2.2. And then y2 is 1/10 times f of x1, y1. Well, there's y1, so, and x is now 1/10, so it's 1/10 times 2.2 minus 0.1 plus our 2.2, so 2.41, trust me on that one. And you can see, I took the time and trouble to do this, but I think you can see what happens. For instance, y7 is 1/10 times f of x6, y6, this being x, that being y6, and x sub 6 would be 0.0006. So 0.6. And then plus our y5, which is here, so, sorry, plus our y6 there if we're trying to find y7. And that will stack up and eventually give us a value of y1 is the 10th, y sub 10, and that says 4.597, blah, 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 blah. So, like, let's compare it to the actual answer. It's not too hard to solve this one. It's linear first order, integrating factor e to the negative 1 dx, so e to the negative x, so not that hard to solve. And I have it solved here at y equals x plus 1 plus c times e to the x. So, and y of 0 equals 2 means c equals 1. See why that's so? If x is 0, then this is e to the 0, which is just c. This is 0, so 1 plus e to the 0, so 1 plus c, and that equals 2, so c equals 1. And then the solution of the initial value problem is x plus 1 times e to the x. And so therefore y of 1 would be 2 plus e, or approximately 4.718281828, and the rest is kind of history. So our approximation was off by one, well, let's say a little bit more than 1200ths. And that's when we use step size 1/10. It was off by 2700ths, actually more like 2800ths, when we use step size h equals 1/4. And so granted it would be tedious, but you can imagine we would be off by even less if we use the step size of 0.01. You're thinking, oh no, but that would be so tedious to do that in 100 steps. But humans probably would never do this in 100 steps. They'd write a computer program and let the program run and take it to 100 steps of computation. All right, I hope you're getting the idea.
Unbelievable!
Great.
Uh-huh.
Okay.